This is a short discussion and application and an example of integration and using it to determine probabilities. So we're going to start out by doing an experiment, right? In probability and statistics, we do things called experiments. In this experiment, we're rolling a six-sided die 100 times and we record the results. And so here's what I get. Right here are my frequencies. So how many times did a 1 come up when I rolled the die? How many times did a 2 come up when I rolled the die? A 3, a 4, 5, 6, etc. So we'll notice that the total is 100. From that, so this is the experiment that I did, I can use those frequencies, how many times that number of dots came up, to predict or come up with a probability based on those outcomes. And so if I take each frequency here and divide it by the total number of rolls, I can convert that to a probability. 18 out of 100 times I rolled a 1. That has a probability of 0.18. And I can do that for each of my outcomes, right? 1 through 6. 1 dot, 2 dots, 3 dots, 4 dots, 5 dots, 6 dots. And I can come up with their probabilities. Now, one thing to notice is that when I add up their probabilities, that the total is 1, right? 100%, right? That's another way to think of this is 18% of the time I rolled a 1. 20% of the time I rolled a 2, and so on. So this 1 is equal to 100% of the outcomes. So that's all well and good, and we have these sort of discrete outcomes, right? I can't roll a 1.5, I can only roll a 1 or a 2 or 3, etc. So let's take a look at this from a graphical perspective. Okay, so I've made this bar graph that shows us the different heights of the bars, so we can see along the horizontal axis here, I've plotted the number of dots, and along the vertical axis, I've plotted their different possible probabilities. And then I've made a rectangle, a bar, for each of the different number of dots. And so if I asked you what is the probability of rolling a 3, I can come over here to the 3 and look at its rectangle, and it has a height of 12 out of 100. But notice also, since these are discrete, right, 1 is very separate from 2 is very separate from 3, if I just calculate the area of the bar, right, and we're assuming these are all 1 unit wide, right, because they can't be 1.5 units, right, it's a space of 1 between 1 and 2, etc. So if we calculate the area, now this idea of area is going to become important in just a little bit, but the idea is the area, so if we added up all of the bars, the areas of all the bars, each bar has a specific percent of the area, right? So if I calculate the probability of 3, I can also relate that to the area of the rectangle or bar that 3 is. And it's 1 unit wide by 12 over 100ths units long. And I get that same answer I got, 12 out of 100, right? Or 12%. That bar makes up 12% of the total area of all the bars. And if I wanted to calculate the area of rolling a 3 or a 4, or the probability of rolling a 3 or a 4, then I would add the area of those two rectangles together or add their probabilities together to get that this is 25, or a 25% chance of rolling a 3 or a 4. Or those two bars make up 25% of the total area of all the bars. That's if we have a discrete set of outcomes, right? 1 is very distinct from 2, there's nothing in between. Happens when I have a what's called continuous variable. So things like height, weight, temperature, time, volume, area, distance, things that we measure, where you don't necessarily get 1 pound and 2 pounds, you can get 1.2 pounds, you can get 1.13 pounds, right? You can get all sorts of values in between those two. They aren't discrete any longer. They're continuous. If we think about the number line, right, between 1 and 2, there's a whole bunch of numbers that exist that live on the number line between 1 and 2. That's continuous, okay? And so when we have that, right, we have lots of different values that a number can take, that our probabilities can take on. And in fact, since there's so many of them, right, if we tried to make rectangles, we'd have so many rectangles, it would be very hard to compute, right? So what we do instead is we connect the dots to come up with a function that represents the probability density function, otherwise called a probability distribution function. That's another name you might have for it. But the one key thing that we talked about before is that if we added up all of those rectangles, their area would be 1. Or if we added up all their probabilities, their area would be 1. That same thing holds here. If I calculated this area, right, for this function, that area under that graph has to be equal to 1, because what are we adding up? All of those individual values, all of those individual y values are probabilities, right? Probabilities. And so if we add them up, if we think about sort of very tiny rectangles, if you will, right, when we talked about areas under the curves, so if we add them all up, this area under the graph had better be 1 also. But we can see we can't really use rectangles anymore, right? Because we don't get nice flat shapes. We've got all these curvy shapes. But fortunately for us, we know about integrals and definite integrals and how they relate to computing areas. So again, we want to remember that this is important. An area under the graph of the probability density function, sometimes called a probability distribution function, is it has to be 1. So if f is my probability distribution function and I would like to compute the probability of getting a value between c and d, right? What's the probability that whatever I'm asking for here for my continuous probability, what's the probability that the average American is between average American woman is between 5'5" and 5'6" tall. Okay, that's kind of the example we would give here. Well, we would calculate that area, which we know how to do, because the area under the curve is just the definite integral from c to d of the function. Okay, so that's how we're going to calculate probabilities for continuous variables, for continuous probability density functions or probability distribution functions. So let's take a look at an example. A cell phone provider determines that the duration t in minutes of a phone call has a probability density function of f of t equals 2e to the negative 2t, and t can vary between 0 minutes, right? Never happens. You make the call and it never connects, all the way out to who knows how long, infinite number of minutes. Find the probability that a phone call will last no more than 1 minute. So I've graphed our probability density function here, 2e to the negative 2t, and I'm going to shade what is represented by phone call that will last no more than 1 minute. So 1 minute is the maximum, so it could last anywhere from 0 to 1. So this is the part of the probability density function I'm looking for, the area, the probability. So the probability that the call is between 0 and 1 minutes is the integral from 0 to 1, 2e to the negative 2t dt. And so we use our skills in techniques of integration. Using the constant multiple rule, the 2 stays. Antiderivative of e to the negative 2t is 1 over negative 2 e to the negative 2t. And we have to evaluate from t equals 0 to t equals 1. Let's see, 2 times negative a half is negative 1, or negative e to the negative 2t from 0 to 1. So we would need to calculate e to the negative 2 minus negative e to the 0. So this is going to be negative e to the negative second plus e to the 0 is 1. So let's try and compute what that probability is. 0.86465, we'll say. So whatever you need to round to, you can round there. So that's the probability. Pretty high likelihood that it lasts no more than 1 minute, right? An 86.47% chance, if you will, that it will last no more than 1 minute, okay? So that's all that is just finding area under the curve. Let's try another. It's the same problem, right? Cell phone provider determines that the duration t in minutes of a phone call has that probability density function, but the question is different this time. Will last at least 1.5 minutes. Okay, so at least 1.5 means it's going to last 1.5 minutes or more, right? And now let's talk about here, we would normally say, well, this is p of 1.5 out to infinity, and if we tried to set this up 1.5 to infinity, well, we haven't talked about how to do that, right? Okay, how do I do that? What? How do I evaluate something out toward infinity? Well, we could apply limits, but another thing we could do is remember the total area, or if we added up all the probabilities, it equals 1, right? So this area that is less than 1.5 plus the orange area would have to equal 1. So what I can do instead is say the total area is 1, and if I subtract the probability that it lasts a maximum of 1.5, I can do that computation. So this will be 1 minus the integral from 0 to 1.5 of 2 e to the negative 2t dt. And doing our computation as before, we know that this is going to be 2 divided by negative 2t, so this is actually going to be plus e to the negative 2t. And then I have to compute 0 to 1.5 on just this part. Right? And if we do that, we can come up with a probability. So we discovered that this is 1 plus approximately negative 0.950. So this probability would be about 0.0498 if we round to 4 decimal places. So a very small probability that it would last at least 1.5 minutes. So we used that key feature that the total area under the curve is equal to 1, and that is really how we solved this problem. Is we said, okay, if the total area is 1, if I take the total area and subtract off this area, oops, not I don't want that color, this area over here, that will leave me my orange area, which is really what I'm interested in. Okay, and so that's basically it. That's the 2 flavors of these problems.